Hi, I'm Ben-Yaakov. This presentation is a short review on a presentation entitled Killing the Bode Plot by Sandler, which was presented at the DesignCon conference in 2016. And this is the first slide of the presentation, Killing the Bode Plot, and it follows by this slide, which is like a tombstone to Bode plots. Well, I personally think this is sort of arrogant and maybe shameful, but this is just my private opinion. But we will see that it's really unfounded. And then there is a slide with some statements about feedback and stability. And it says that a stable control loop is one that doesn't oscillate. It shows here the relationship. This should be a closed loop gain, and this is open loop gain, and this is of course the loop gain. And then it says that unity gain negative feedback result in a denominator of 0, which is unstable. That is, when this is -1, then 1 minus 1 makes the system unstable. Okay, let's go back a little bit to the fundamentals of control and see what are the real facts here. So here is a feedback system. This is the plan, this is the feedback loop, and the transfer function between input and output is of course this open loop gain times 1 plus beta A open loop, when this product is defined as the loop gain. Now this of course can be represented in the general case, you can say in Laplace transform, as a numerator over a denominator. These will be polynomials in S. And the only reason why a system, a feedback system, will be unstable, this is the only reason, there's just no other reason, that there are poles or solution to this denominator which are in the right half side of the complex plane. That is, if we have a solution here, the pole here, then this system will be unstable. Why will it be unstable? Because if you solve it, then in the time domain, you'll get a term like E plus t k, well, t is time, so this is diverging, it's not converging, and therefore the system is unstable. Now there is a private case in which the solution is here on the j omega axis, and this is an oscillator. So this is a private case, this is an oscillator. But in general, instability means poles in the right half plane. So how would we know if we have poles at the right half plane? And here Nyquist is coming to the rescue. This is the Nyquist plot. This is now vectors, or the x's are the imaginary of the loop gain and the real of the loop gain. This is the loop gain, and we're talking about the imaginary part, the one axis, and the real part. And this is actually the loop gain. It's a vector. It's a function of frequency. Starts from frequency 0, goes all the way to infinite, and then from actually minus infinite frequency goes to negative frequency to complete this circle. Now the Nyquist criteria says that if this circle does not encircle the -1 point here, then the system does not have poles in the right half plane. Well, this is not exactly. There are some exceptions. There's a question of whether there is or isn't a 0 at the right half plane. I'm not going into all the very fine detail. I'm just talking about the basics here. So for a simple system, nothing special about it in terms of the zeros, this will be correct. That is, the system will be stable, no poles at the right half plane, if it is not encircling. Now, if we look at this plot, we see the following. We have here now, I have plotted the unity circle. This is the locus of all the points that are a distance of 1 from 0. So this is, for example, a vector of 1, so the magnitude is 1. And here we have a penetration. This is the penetration of this plot, the Nyquist curve, into the circle here. Now, this is very important. And this point, or how far or how close it is to the axis here, is actually the phase margin that tells us how close we are to trouble. That is, if the penetration is here, then we have a very small phase margin, and one can show that then the system will be with high Q, oscillatory, etc. But there is another point here. By looking at the penetration point, we can tell as whether the curve is actually encircling the -1 point, because if the penetration point is here, then obviously we'll have something like this. Here's the penetration point, so we are encircling. So this penetration point here, this one or this one, is a very important indication as the system, if the system is stable or not. Now notice that in this case, this is an unstable, the red one is an unstable system. These vectors are 1. This is not this case. The value of these is not -1, because the -1 is only here. So this is a vector of 1. The system is unstable. So this simplistic notion of just having 1 - 1 makes it unstable is just incorrect. So in fact, you can have here any number, a positive number or negative number, and the system would be either stable or unstable depending on this situation. This plot is a vector plot, and this vector has actually 2 parameters to it. It's the size, the magnitude, and the phase. So what Bode plots is actually doing, spreading it into 2 curves. This is one curve, this is the magnitude, and this is now the phase. And now, very important, look at this unit circle. This is the distance of 1, and this is exactly this line here. This is 0 dB, meaning magnitude of 1. So this point here is actually this penetration point. So if we look at the penetration point here, and then look at the phase, we can tell about the phase margin, and that's the stability criteria is all about. Okay? So basically the Bode is just another way of looking at the Nyquist. It's just a different representation, which at the time was very convenient because these plots were done by hand, and this is much easier to do by hand. Now today, with computers, you can plot the Nyquist very simply. I mean, even with simulation, you can get it immediately. So there's really no problem in plotting this curve, but still we are used to the Bode plot, so this is why it is so popular. So let's go back to these statements. Says that a stable control loop is one that doesn't oscillate. Well, this is incorrect. Instability or instability is related to poles in the right half plane, and the notion of having here -1, which says here, is just incorrect. I mean, it is correct, but this is just a private case, but it's not sufficient. There are other situations that the system will be unstable, even it will not be here -1 as we have seen before. So this statement is just incorrect. And then it says Nyquist is better assessment tool for stability than Bode. Well, I don't think so. They are just about the same. And of course, there's no problem in plotting Nyquist if you wish. So let's move on with the presentation and go to this slide. What we see here is this box, which is Omicron. It's a network analyzer or vector network analyzer. And then there is one probe here. Doesn't say what it is. This is apparently made by the company. And then it shows here a linear regulator, which is split into 2 parts. This is the capacitor, and this is the regulator. And then it marks here the impedances that you look at the capacitor, then you look into the regulator back. And it's not clear whether the measurement is made by splitting really these 2, because if you split it, then this system may not be stable. And of course, if it is a switch mode converter, then the ripple will be unacceptable because you don't have a filter here. But let's not worry about it now. Let's just go and see what it says here on the slide. It says you can measure phase margin from single measurement, just a single measurement, which entails impedance magnitude, phase and group delay. Okay. Then it says that what is measured is Z sub S and Z sub L. Here it is, from which the stability margin is obtained, and the phase margin of the system is obtained when this ratio of Z sub S, Z sub L, this is these impedances, the ratio of these impedances is equal to 1, and look at the phase. Okay, so again, let's have a look at the fundamentals of all these expressions. Professor Middleburg, many years ago, looked at the problem, which is very important, the interaction between a filter and a converter. Well, as it turns out, if you have a DC or any other converter in closed loop, and you look at the input, then the incremental impedance or resistance is negative. Well, the reason is that the control is keeping this voltage constant and the power is constant. So as you, for example, increase the voltage, the current will go down because the power is constant. So the incremental impedance here is negative. When this negative impedance or resistance interacts with a second order system like a filter, it might oscillate. So there is a problem of designing the filters in such a way that it will do its job, but then it will not cause instability. So this is the question that Professor Middleburg, the late Professor Middleburg, has looked at. And since then, there have been many papers on that, on various aspects. Now, the way it's been treated, and this is a very neat, very clever way, is the following. You take one block, this could be a filter, it could be another converter, it could be anything, and express it or present it as a gain block and an output impedance. And then you take this block and present it as a unit with an input impedance and then a gain block. Now the transfer function between V in to V out will be V in times G, here it is, V in times G. Then you have a voltage divider, Z sub L over Z sub L plus Z sub S, times F, that's the output, or V out to V in. These two are multiplied, and then I'm dividing it by Z sub L, and I'm getting this expression. Wow, very interesting. It looks like a feedback closed loop expression. So this ratio of these two impedances is the loop gain. And indeed, this has been called since then the minor loop gain. So it's a minor loop gain. There's this system loop gain, might be more than one. There are many other minor loop gains. So this is one of the minor loop gains of the system. It has been shown that you can apply the Nyquist criteria, or look at it in the Bode plane, for this expression to tell whether there be the system in this respect will be stable or not. Same criteria. And as I've said, there are many papers on this issue, not only at the input, but people have also looked at expressing the relationship between a converter and a load, which is kind of getting closer to what we are talking about, as these two impedances. Okay? So for these two, you can also set the criteria of stability. And here, there's a paper, the same paper as before, by Lee and Lehman, 2004, and here they're splitting it into this capacitor and this system, which is a converter, but as I have said, this could be any other system. This is just the interaction between, you might say, two blocks that you can look at the stability, or this, you can look at it as a minor loop. Very interesting. Now the question is, of course, is the minor loop gain is a source of information on the robust stability and transit performance of the system itself. That's a major question. That is, we understand that the minor loop is telling us about stability, but can it tell us something about the system itself? Now, this is a paper by two prominent researchers from Finland, as a matter of fact. They are control people, and they have here some conclusions. In the abstract, let me zoom at it, and it says the following. According to the investigation, the system level minor loop gain measured at an arbitrary interface, could we say the output, does not necessarily contain any other information than the existence of stability. So you can, in general, you cannot use the information of the minor loop you cannot use it as an information about the system itself. This is a very important conclusion. So let's go back here and see what this presentation is really stating. It says that Nyquist solves our problem. It's not always simple to compute. Well, I've already said that's not correct. Today, with a computer, you can plot Nyquist without any problem. Now, it also says that the method proposed in this presentation accomplishes the same thing more simply through closed-loop outer impedance. Well, as we have said, it doesn't do anything the same. It just says about stability, and in some cases about the system loop gain in very special cases, but certainly it's not replacing neither Nyquist nor Bode. And then it says that this approach determines control of margin without needing access to the feedback loop. Now, this is correct. You don't need any feedback, but it doesn't tell you necessarily about the phase margin, because in general, it is just telling you about the minor loop gain. And then it says that the method is based on proven minor loop gain theory. Well, I don't think that's correct, because the theory says just the contrary. It says that you cannot use the minor loop gain as a measure or as an indication of what is really happening in the system in the general case. So there's no theory here, nothing new. I mean, nothing has been refuted from what is known in the publication up to date. So the question is, are there any examples, at least in this presentation? So let's have a look at it. So I'm going back to the presentation here. This is the first slide. This we have seen already before. Well, here's the first one, and it's a linear regulator. This is simulation. I don't know whether a hardware experiment was also conducted. All we see here is a simulation. And what we see here, we don't see the splitting. We see just an injection of a current here, 1 amp. In simulation, you can do that. And this is very similar to the method that I've shown in one of the videos in my YouTube channel. By injecting here, you can get the output impedance, and if you know the impedance without feedback, then you can calculate also this, get information about the loop gain of the system itself. Anyhow, here, what we see is an injection of 1 amp. This is the Bode, and this is what is measured by the method proposed. Again, it looks as if this is a simulation because it's an AC source and etc. We don't see any hardware involved here. So let's have a look at another example. It's again a linear regulator, and some measurement of the Bode plot. I don't know how they were obtained, and there is a measurement of the made by this system, and they're talking about the phase margin being measured the same. Again, this is a linear regulator, and I'm not sure if it's a hardware measured or not. And then there is another example, which is a linear amplifier, and again, it's not clear what was measured and how the data was actually processed. And what is claimed is, of course, that you get the same thing with the Bode plot and with this system. Bode plot is not available in this case. I don't know why it is. And then there's some sort of a summary here which says that the proposed approach is applicable to op-amp, voltage regulator, voltage references, audio amplifier, system level, box-to-box stability, current regulator stability, almost any controller. Well, we haven't seen here anything about switch mode converters. And of course, one has to qualify all this by the fact that the minor loop gain, first of all, it's not new, it's well known, but it really doesn't tell you necessarily about the system. That's the end of the presentation. There are no references here, as if everything has been sort of invented here, and that's the end of it. So let me present my conclusions. First of all, the output impedance minor loop theory is really well known. There's nothing new here. It has been published in many, many papers, discussed, analyzed, etc. The shortcomings of it are known, as well as the benefits. There is no theoretical basis to the claim that the proposed method can be really a replacement for Nyquist and Bode plots in the general case. This has not been shown, proved, or verified. Now, the usefulness of the method for switch mode converters analysis has not been proven or even shown. So how would you use it for switch mode converters? And then the usefulness of the method for switch mode converter design has not been proven or even shown. Now, Bode plots and Nyquist are used for the design phase. You start with the open loop response, you design the controller, you see the combined closed loop response, and then you can modify it and improve on it, iterate on it. Now here we are talking about a post-mortem measurement after a system has been built already, and that you see whether it's stable or not, and then, well, you'll go back to the design phase if it's not good enough, and use Nyquist, Bode plots in order to correct it and to redesign it. So my conclusion would be that Bode plots are really alive, and they are doing well, very useful, and they're going to be here for a long time. This brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.